Hi everyone, and welcome to another instance of Math Research Live with me, Charlotte Aten. As you may remember from previous live stream, my lighting situation isn't the best in here, and I don't have any fancy lights, and so I will be a little bit dim until the sun sets a bit more, but that'll be okay. I hope you've all been having an awesome week, an awesome summer, if you're on the half of the earth that I am. Well, yeah, I hope it's been going really well. So this week I figured that I would talk about the paper that I actually talked about the first time I ever did one of these live streams, because while there's still a lot left to do with it, I hope to actually get the edits done that I want to do by the end of the summer. And I figured that actually today's topic, which specifically is trying to improve the main theorem in that paper, should be kind of good thematically to follow with what I was messing around with the previous time, which had to do with presentations of algebras or free algebras or something along those lines. So, well, since you can't see me very well anyway, maybe I'll just pop over to this monitor. So, if you'll recall, and I have linked in the chat as well, what I'm talking about is this paper. If I can find the right amount of room for it, and so you can already see whatever the current state of it is on the archive, but there's definitely some improvements to be made. It's been a very long review process, and I hope that I haven't actually let it go too long at this point again, but hopefully it will be published soon, and it won't be too much longer than it already is, yeah. So, and I'll remind you of some of what I'm going to be talking about too, although I can't really do the whole paper because, it's a long paper, it'll take forever. But you can peruse it at your leisure, by following the link to the archive. And so, well, I will actually perhaps take a little bit of a look at the overleaf here. I'm not really sure that I will spend a lot of time messing around with the overleaf, because I think I'm just going to try to improve this proof by hand, just to make it more visually appealing. Here, maybe I can make this as visible as possible, though. So there's still a lot of changes that need to be made, in particular with respect to notation, and that's what I hope to clean up. I think that the reviewers just found the proof of this to not be especially readable, and so so my goal is to do that, actually, is to make it a lot more readable. And as always, feel free to ask me questions, and probably I will be happy to spend time answering your questions, or get drift off on whatever kind of digression it results in. I maybe can't just explain the whole paper from scratch every time, but feel free to ask about anything in particular, and it should be pretty cool. Oh, and before I really get into it, I also wanted to mention that as I've mentioned before on this stream, I'm not going to be in the U.S. For the next 2 Mondays, and because of that, it's looking like my time zone will make it that this time will be early in the morning on Monday morning for me, which probably will not be ideal. So I'm thinking probably I'll do reruns, in which case my partner will monitor the chat, will moderate the chat as it is live, because you can still chat live on the reruns, or maybe this is a little bit out there, but if somehow miraculously I manage to have enough time to, maybe I'll record just some pre-recorded other videos of things, and I'll just kind of debut them there along with the chat, and then you can still chat live, but I'll just be slightly more imaginary than usual during those ones. All right, well, this currently it's theorem 10.7 in this draft, apparently, the draft is getting a bit long. The one on the, let's see, the thing on the archive, the current version on the archive, I think was only 49 pages. But as you can see, as things progress and details are filled in, we're at 66 right now. But I really hope that this is under 100 pages when it's finally published. You know, because like it's okay if it keeps adding a little bit more and a little bit more over time. The big problem is, you know, if little bits of the paper are added too quickly, then it will, you know, it won't be a convergent series, and the paper will just grow, you know, without bound, and it will never be published. But I hope that that's not the case, and that this is actually published in the not too distant future. All right, so. Well, maybe first, before anything, I should just remind you generally what this paper was about. So the idea was if you have, you know, if you have some type of arithmetic operation where you have some notion of how to multiply or combine things, then you can make a triangle. Okay, maybe I'll try to make a better triangle. You can make a triangle, and the triangle represents the fact that, say, A times B is equal to C. And so the idea is that you make those three things the vertices of a triangle. And as an extra kind of bonus, we can think of maybe these as being like the inputs, and maybe I'll underline those. And we can think of this as being like an output, so maybe I'll overline it, or overline this, just to remember which ones are the inputs and the outputs. And if we assign an orientation to this, then it's basically telling us that maybe this is the first input, this is the second input, and this is the output. So we can think of this decorated triangle as being like the fact that A times B is C. And so for reasons that, well, I can go into if people want to ask about them, but the idea was, well, if we have a non-commutative, well, we don't really need finite, but you can think finite, but if we have a non-commutative group G, then we can think about actually sending that to something called a pseudomanifold. And I'm sure I'll spend the rest of my life misspelling the pseudo part of pseudomanifold. But we can send that to a pseudomanifold, and that pseudomanifold is, well, in this case, if we're using a group, it's a bunch of triangles, and the triangles represent what I already just told you, like things like the fact that in this group, A times B is equal to, you know, some C, or I'll just maybe write AB, and over here, so going the one way, A times B is AB. But if we think about a triangle going this way instead, actually, let me make sure that, I guess this would be the compatible orientation. It goes up there, it goes down there. So here's the opposite product, B times A, and for some technical reasons, I don't want them to be the same. So A times B is something, B times A is something else, and these orientations help us keep track of which is which. And there's even more to it because, well, if we had something else over here, which, if I could draw a triangle better, that would be nice, where when you multiply B by that, you get AB. Oh, hello. So when you multiply B by something, you get AB. Well, actually, we can figure out what that is because, well, if I want that B times something is equal to AB, that means that we just have to conjugate A by B, and that's the thing. So this would be B inverse AB, and we could similarly, the picture gets harder to draw, but we could similarly make other triangles like this, and we'd get some kind of, you know, sequence of triangles. And the reason it's a pseudomanifold is, well, it's not really a manifold, because when you do things like this, you don't necessarily get a bunch of triangles in the shape of, a sphere. If you can think of the sphere as being like made of triangles, like for instance, you can think of like the tetrahedron as being like a sphere made out of triangles, or even an octahedron, which I'm worse at drawing, although I'll try, just so that we can all watch me struggle to do that, because that's always a good time. All right, so then you can pretend that I actually drew an octahedron here. There it is. You can think of these as sort of being like collections of triangles that make up a sphere, or similarly, you could even think of it being like collections of triangles that make up a donut somehow. But when you do this, what you'll find is that you don't always just get something nice like this. You sometimes get things that have pieces that don't quite look like 2D space close by. If I can actually draw this a little bit better, let's see. So sometimes you get things like the pinch torus, where it kind of looks like a donut. It looks like this tube that comes back to itself, but here it just pinches down to this single point. Like you just sort of took like a little piece of it and just like collapsed it to a single point. And so this is not locally Euclidean at that point. So this makes it not a manifold, but it is a pseudo-manifold. I'll just not finish writing manifold to save space. So you can make something like this, and then maybe I won't get into it this time. I talked about it a little more last time, but then you can get an actual manifold by doing what's called desingularizing this thing. And one of the big contributions in this paper was that as far as we can tell, nobody had ever described like a nice like functorial desingularization for pseudomanifolds of dimension higher than 2 before, and so we had to do that in order to do sort of the analogous construction in 3 dimensions and higher. Yeah, so that's a thing. It's a big part of the paper. Maybe I won't focus on it too much today, but basically you can get you can then somehow do some other stuff and get an actual manifold from that pseudo-manifold that you make. And so yeah, well, I won't actually get to the doing calculus on manifolds part of this today, probably, but there is, the part of the process of doing this construction of getting an actual manifold involves endowing the pseudo, or well, okay, you can make a manifold from the pseudo-manifold, which is not the final one, but is sort of an in-between stage, and you actually have to endow that with a structure, a smooth structure that would allow you to do calculus on it, and the use of that smooth structure is important in constructing the final manifold. So although this isn't too directly related to calculus, there is a step in this process that you do need to know at least something basic about doing, how to set up manifolds to do calculus on them. So yeah, so it is there somewhere, and in the future, going forward, I would like to actually maybe understand, geometric properties of these things a little bit better, which would involve more calculus. But at the moment, I'm just going to be satisfied to have the basic setup. But yeah, thanks for checking this out. I hope it's a healthy distraction. All right. Well, actually, why don't I just go to a new page and make more room for myself? Okay. Oh, and this is also the first stream, by the way, just to remind you. We have those donut emojis now that are like the 3-hole donut, and so we have these emojis now, and well, this is actually the first talk where the emoji is actually relevant, because I'm talking about manifolds. So in other talks we've had them, but this is the first one where they're actually going to be something useful. Yeah, I feel like my connection's pretty good at the moment, but yeah, I'm not sure. I have a little green box in my interface, which I believe indicates that it's a good bit rate. but I don't know more than that. Okay, so what was so I was advertising the donut 3-hole donut emoji. More emojis coming soon. Definitely we want to do the Dobby one at some point, because that's it's a very good suggestion that people have had. I think he's around here somewhere. He's just chilling. He's just chilling on the floor. I think he likes that we have carpet now, so he can lay on the carpet. Okay, so what's my goal? What's my goal for today then, or what am I going to at least take a look at? Well, here's kind of a natural question. So I claim that this process that I described, although I didn't give a lot of details, I claim that this process that I described, that it allows you to construct manifolds, which are things like this that, in at least the 2D case that we're considering maybe at first, are things that look like donuts with many holes, And maybe they can have some other pieces that look like spheres or that type of thing, but basically that's the situation, Donuts with various numbers of holes. The sphere is a donut with no holes. It's the donut hole. But that was it's more of a joke about the food donut than an actual mathematical thing. But yeah, the sphere is like the donut with 0 holes. It's a genus 0 surface. And although I won't belabor it too much, actually, for what it's worth, I also am allowing in this construction for us to have surfaces that are unbounded. So we could also, in principle, have things like a sort of infinite kind of tube here, like an infinite cylinder that just doesn't really have an end and just goes on forever. That's definitely it's allowed. I'm not going to really belabor it too much, but I want to do everything with keeping in mind that we're allowed to have things like infinite tubes that go off forever, or something like a donut that has a part that's like a tube that just kind of goes off forever. That's also allowed. And the tube just keeps going. Okay, so a natural question is, if I can make things like this, a natural question is, can I actually make any possible shape? Maybe let's just not focus on the infinite ones, although I do want to allow infinite ones in general. Can I make any possible shape by doing this process? Like, in other words, I know that I can make certain manifolds by this process from doing examples, but how do I know that, like, for instance, like if I ask for like a 45-hole donut, how do I know that I can actually make that? By choosing some finite group, or in the more general construction that we have, some instead of non-commutative group, we'll replace this with quasi-group, which is just the non-associative version of a group. And it's a natural question. Can we actually make, say, the 45-hole donut this way? That's a reasonable thing to wonder. And of course, given any finite amount of time, we can only check so many examples perhaps, although we could come up with infinite families. And indeed, in a previous paper just about the 2-dimensional version of this with groups, the authors of that paper, one of whom is my PhD advisor, did actually find for groups that there were certain infinite families of genuses that were constructible by just using this construction for the 2D version. But it still left open the question of a lot of different possible genuses. So A and B are not numbers in the classical sense, although you could use the quaternions, for instance, which are non-associative. So if you remember, for the real numbers, multiplication is commutative and AB equals, BA. For complex numbers, if you have like A plus B I, times C plus DI, if you follow through the rules, you'll see that that's actually the same thing as C plus DI times A plus BI. But in general, if you go to the next one of these Cayley-Dixon algebras, the quaternions, which aren't. It sounds a little fantastical at first, but the multiplication for these, which you might consider to be numbers, is non-commutative, but it obeys all the other nice rules of algebra that you would like, and these are actually quite useful. People really advocate for them in representing rotations in three-dimensional space, but these are numbers of the form like a plus bi plus cj plus dk, where the rules are that I times j equals k, j times k equals I, and k times I equals j. But if you go the other way, you pick up a minus sign, so j times I equals negative k. Let's just pretend that's a k. I'm not good at writing the letter k. K times j is minus I, and I times k is minus j. And so I know it seems maybe kind of surprising, but these actually turn out to be quite useful. And they actually give us one of our first examples of a shape that you can make using this construction, because if I start making triangles like I described, I can do I times j, and I'll get k here as like my output thing. But notice that if I do j times minus I, assuming that minus signs work the way that they do in other systems, so j times I would be minus k, so presumably j times minus I would be k, and so then we'd have that, and then minus I, times minus j for similar reasons would be k, positive k, and then minus j times I, again for similar reasons, would be positive k, and so we get kind of this square sheet. And if we go over and do the opposite ordering, where instead we do j times I, then we'll get minus k as the result. But that's the same as if we did I times minus j. And similarly, if you go around, minus j times minus I, and finally minus I times j, that would give you minus k too. So you get these two square sheets, which aren't the same because one has minus k in the middle and the other one has positive k in the middle. And so if you look, if you go around the outside, it's like ij minus I minus j, ij minus I minus j. So these two pieces fit together along this square, which is like I j minus I minus j, and they fit around this square and they make like this like octahedron. And now again we're going to pretend that I can draw an octahedron, because even if I was doing it on paper on a blackboard by hand, I wouldn't be very good. Oh, that's really atrocious. Okay, I'm too embarrassed. I'm going to erase it. Anyway, I drew one earlier, and I'll show you. You can imagine that those could kind of stick together to make this octahedron, whose equator is ij minus I minus j. Where is my octahedron? Okay, this is my really incredible octahedron. Okay, so the equator is like ij minus I minus j. And then the north and south poles are like k. All right, I'll try to write the letter k a little better, like k and minus k. And so you could think about that little octahedron as actually representing this particular part of the non-commutative multiplication of the quaternions. And so you can do this. You can do this for other members of the quaternions as well, or other multiplications in the quaternions, and you can make a manifold from those. Of course, if you use all the quaternions, there are infinitely many, and so you would end up making something that was infinite or had an infinite number of triangles in it. But there's also a quaternion group whose members are just these i's, j's, they're negatives, and also plus or minus 1. And you could make just a finite thing from these. Yeah, I'm not sure specifically what you remembered or what you might have read about the Riemann sphere, but of course the Riemann sphere is a way of thinking of the complex numbers, maybe plus there being some point in infinity, and yeah, I mean you perhaps could think about the quaternions similarly if you added a point at infinity. I actually am not super big on quaternionic analysis myself, though, so I'm not really sure of the benefits of doing that. But it's definitely a thing. I wouldn't be surprised if there was a version of the Riemann sphere for these as well that people actually found useful. I just don't happen to know anything about it myself. But yeah, I mean, definitely. This is this is kind of the complex analysis is like it's too real dimensional. In some way, like this is like the next level where you have this 4-dimensional thing and it has the real part and the complex part and then it has this other part and this is if you want to continue, this is part of a general family of things that are called Cayley Dixon algebras. So I'm gonna leave it at this one though. Yeah, so that's okay. I ended up doing an example of the construction, but that's an example. So if you have some kind of multiplication like this, it doesn't have to be that closely related to the real or complex multiplication. But if you have some kind of multiplication like this that's not commutative, then you can do this construction and you can make some shapes. So there's actually an 8-element group whose members are plus or minus 1, plus or minus I, plus or minus j, and plus or minus k, which is the quaternion group of order 8. That the multiplication of those is just the multiplication that I described up here, and 1 and minus 1 work in the way that you would expect. And so if you do this construction to this group and form what we call the serenation of this group, then what you'll get will be the disjoint union of actually 3 spheres. Each one of these is like the octahedron that we looked at before, but there's 3 of them as it turns out. So we can get certain manifolds, like for instance we can get a sphere, or 3 spheres, but whatever. We can get one of the pieces to be a sphere, so we know that a sphere can definitely be made by doing this construction that I've sketched here. But so for sphere, maybe we can put a check mark. Yes, we can make a sphere. And then if you start doing other examples, you can say like, okay, we can do something similar, and I can find one that has a torus as one of its pieces, or maybe a 3-hole donut, or whatever. And it's natural to ask, like, can we find maybe some finite, maybe I won't even say finite, although I do want to add that in at some point. Can we find some group, at least, G, so that when I do this construction, this serenation construction to G, we get, maybe the, genus, I don't know, I'll just say little g. No, that's kind of confusing with the group G, but the genus, I'll just say N, I guess, surface as a component, so that, okay, so that I guess I trailed off in my sentence here. So that this construction, when we do this construction to the group, can we find some group so that this serenation, this manifold that we make, has a genus and surface as one of its components. Okay, so if you choose an n, is it possible for me to actually make a surface that has is it possible for me to choose a group? So in other words, like you give me an n, like you say, I want to make, like you can say, I want a 45-hole donut. And then I should be able to say, well, if you look at this group, then if you do this construction to it, this serenation construction, then you do get one of its pieces as a 45-hole donut. That would be nice. So can we do this? We don't know. So we still don't know whether it's possible to pick an n and then choose a group that will give you a surface of that genus as one of its pieces when you do this construction. We don't know. We do know that certain infinite families of genuses are possible. So I don't remember what they are, but we know something along the lines of like, we can get, certain infinite families, and so we can get something like, and I'm not gonna look up what the actual lists are right now because I don't have it memorized. We can get something like genus, maybe you can get like genus 0, like 1, like 3, like 47, like 82, like 96, like blah blah blah. There's some kind, I don't know that these are the actual numbers, but this is just, something like what it is. We have infinite lists of numbers for which if you choose the number of holes to be that one, then we can find a group that when you do the construction to it will give you a surface with that many holes in it. But other than that, we don't know. Like we don't know about that. So as it turns out, actually, one part of this that makes it really hard is that we have to, if it's going to be a group, it has to be associative. Like that's part of what it means for it to be a group. In other words, we're asking for it to be a group. So, A times B times C has to be the same thing as A times B times C. And although that's a very useful property that has lots of interesting consequences throughout all of math, this property is actually a bit of an obstruction here because it makes it way harder to answer this question. If I throw away associativity, I can answer this question. And again, just feel free to ask if you have any questions or comments. Because that's also part of what makes these so fun. But okay, so I can answer this question if I am allowed to get rid of associativity. Oh, buddy, it's okay. Someone's probably just living their life out there. He got spooked. Are you okay, Debbie? There's a lot of other dogs here too, so sometimes he's curious about the dogs. Okay, so what about the same thing where can we find no, it's okay, Dobby. Hey, come here. It's okay, buddy. You're okay. You're okay, bud. Right. So can we find a quasi-group? Well, maybe I'll call it Q for quasi-group, so that the serenation of the quasi-group has so that it has a component of genus n for just whatever given n, and the answer to this is yes, we can. And so actually I can do even better than just yes, we can. Come on, buddy. It's okay. It's all right. Just chill out with it. It's okay. There must be a lot of people out there or something. Okay. So yes, we can. And what's even better is we can even choose Q to be finite, which actually, even though these donut things look like, okay, it's kind of finite in the sense that it doesn't go on for, I just started drawing one of the same genus I just did. It doesn't really look like these go on forever, They kind of look finite in the sense that you could make an object like this that you could hold in your hand. And you might even buy that, well, I should be able to make a shape like this. If I make it a little more pointy, I should be able to make a shape like this out of a finite number of triangles. You'll probably buy that, I can somehow assemble a bunch of triangles together to make, the surface of one of these things. So, that's a reasonable thing to think, but it's not entirely obvious that even if you could choose some multiplication rule, some non-associative multiplication rule that had one of these things as its component, it's not really obvious that the multiplication rule has to be on a finite set. For instance, I actually described previously these pieces for the quaternions, and although there is this finite group that is the quaternion group of order 8, for which the construction just gives you these 3 spheres, those 3 spheres are part of the construction applied to the whole quaternion algebra, which is infinite and includes elements not just like these, but also things like, 3i minus 4k and other such things, of which there are infinitely many. And so, these 3 spheres are sort of this one nice little piece of something which is really infinite. And you might ask, well, it's not obvious that it's possible to choose a finite quasi-group, but it turns out it is. So that's actually very nice. And fortunately, other than interpreting the result in our context, there's really not actually too much to do here as far as a proof, because this follows from, I'm sure I'm going to pronounce this incorrectly. I think I can actually spell it correctly. Smetaniak's theorem. So this is from the 1980s, and so this was the resolution. If I could spell resolution, that would be good, I guess. This is the resolution. Oh, I'm not done with the parentheses. Of the Evans conjecture. Okay, and so I'm not, I guess, going to state what the actual conjecture was. It's not that it's super long, but it's just a little bit of an aside. But this theorem, so what this theorem implies, so this theorem implies something that is what we need, but it's actually a bit weaker than the actual theorem. It implies that every finite partial Latin square can be embedded into some finite, complete Latin square. Okay. And so, if you're not as familiar with this, it might not make it obvious, why this is enough, or why this is helpful to us. But the idea is the following. Well, say that I'm not going to do a whole manifold because it's a little tedious to do the whole triangulation as an example. But say that I wanted to have this assemblage of triangles be inside of my shape when I did my construction. In other words, I want to find an algebraic structure that has these 3 triangles inside of it like this, and just pretend that it's a prettier drawing of 3 triangles. Well, how would I do that? Like, how could I make that happen? Well, okay, actually I'm gonna do 2 because I realized 3 is actually a little bit much. Okay, so how could I make just two triangles like this happen? Well, of course, I could just have a pair of elements, you know, A and B, that don't commute with each other. That's kind of the basic part of the construction, right? Like that I can have this. But I'm going to do something that generalizes a little bit better, and you'll start to see how I can make any kind of shape that I want in some sense. So what can I do instead? So imagine that this is maybe part of the triangulation of some, like, you know, some torus or some like bigger surface, right? Like this is a little piece of, you know, this is like a little piece of some donut, you know, and the donut has these triangles on it, right? Well, what I could do is I could say, you know, maybe these are like A, B, C, and D. These are vertices of the triangulation. Then what I could do is I could say, these are all of my input things that I'm going to multiply together, and I can make a new thing for each of the triangular faces. I can do what's called the elementary subdivision, where I just add a new vertex in the middle, and I make some new triangles. And what I'm going to do is I'm going to declare that A times D is this new thing, which I'll call maybe, well, I'll do A and C. I'll do A and B first. Okay, so I'll say A times B is this new thing that I'll call X, that goes here. That's an output type thing. And then maybe I'll say that B times C is also X, so that those should go together. C times A is also X. And then I'll say, well, similarly, I'll say, you know, B times A is maybe some new thing I'll call Y. B times D is also, or let's see, B times A times D is also Y, and D times B is Y as well. Okay, so if I could come up with a quasi-group, or even a group if I could make it associative, but I'm not gonna force myself to make it associative. If I could come up with some multiplication table that had these multiplications in it, and was a oh, I need to move this over a little bit. You can complain if you can't see because I'm off of the screen a little bit. Okay, there. So if I can come up with some kind of multiplication rule that has these things in its multiplication, and it's a well-defined, you know, non-associative group or quasi-group multiplication, then I'll be in business. And so the question is, well, if I have a table like this that's supposed to be like a multiplication table, you know, A, B, C, D, and my new things I added, X and Y, you know, A, B, C, D, and then X and Y, you know, a natural question is, well, if I put in some of these entries, A times B has to be equal to X, B times C is X, C times A is X, you know, and maybe I'll put dots where there's nothing filled in, you know, if I do that. And then I say, okay, B times A is Y, so actually that one gets filled in. And then A times D is Y, and then D times B is Y, so those are the ones I have filled in. And then like all the rest of this is blank, you know. Is there some way of filling in this table so that it will still be a Latin square, or that it will still be a quasi-group? In other words, is it possible to do this kind of Sudoku puzzle where I have to start with this and all the other things are not filled in, and I have to put into each of the spots as one of the symbols, or maybe I can add in new symbols if I need them, like maybe I can add in a Z or a W or whatever, but can I add in maybe some new symbols and do this so that each row and each column has exactly one of each of the symbols in it? Like that's a reasonable question. Is it possible to do this? And so the answer in the case where you have a finite beginning to your puzzle, the answer, because of this theorem of Smetaniak from the 80s, the answer is yes. You can actually figure out how to extend this using only at most finitely many new symbols to a complete Latin square. In other words, you can fill in all the rows and columns, you can solve the puzzle, and that will give you the desired quasi-group Q from this question, assuming that you get that initial partial Latin square from the multiplication. Okay, yeah. So Latin square. I did mention it briefly, but let me just show you what I mean. So so a Latin square is an array of symbols where, I'll do a really small one. A Latin square is an array of symbols where there's exactly one of each symbol in each row in each column. So for instance, I'll do a 3 by 3 one. So maybe A, B, and C. B. Let's see, B, A, and C. No, that is a bad choice. Okay. B, C, and A, and then maybe C, A, and B. Okay, and if I didn't mess up, in each row there's exactly one of each of A, B, and C. There's A, B, C, A, B, and C, A, B, and C. And then in each column there's also exactly one of A, B, and C. A, B, and C, A, B, and C. So, so Latin square, so it's a square where there's you know, it has to do two things. Each symbol appears exactly once in each row. And each symbol appears exactly once in each column. So that's what a Latin square or a complete Latin square is, where this is all filled in. And so here I showed you this is a 3 by 3 one, and there are bigger ones as well, and there are smaller ones, although the smaller ones are maybe not as exciting. But yeah, that's what a Latin square is. But this also has, so this is sort of the combinatorial version. There's also an algebraic version of this, so maybe I'll just over here be like, this is the, you know, maybe if you're feeling more like you're doing combinatorics, then you can think of it like this. But there's also a different way to think of it, which is, you know, equivalent in some sense, and that's you can think of it algebraically. And so, well, I'll say the algebraic way of thinking about it in this instance, or we have a different name for it, and we call it a quasi-group, or quasi-group if you prefer. And so the algebraic way of thinking about these things is that you have some underlying set. Oh, maybe I'll use Q for quasi-group. So you have some set Q and some kind of multiplication rule. Maybe I'll do a little star. And so, for instance, in the previous example, we could think of Q being the set of those three symbols, A, B, and C. And we could think of the star as being a multiplication whose multiplication table is this table. Or in other words, basically the Latin square is the multiplication table. And so you might say, well, what's the point of thinking of it as a multiplication table? What benefit does that give us? But the idea is that, well, you can just think of the array of symbols itself, like in this little Sudoku-like picture that I drew up here. Thinking of it as a multiplication is more natural if you're thinking about doing algebra and understanding like the algebraic structure of this. So for instance, if I just think of it as an array, it doesn't really make any sense to ask like what happens if I do like A times A or something, right? That's not really a question that makes sense. Yeah, a Latin square is a Roman who doesn't like to party. That's absolutely right. Now, my partner is also want to call these Italian boxes. So I'll leave it to you whether you're going to consider that to be a synonym, or whether it's just going to be a synonym, or whether you consider an Italian box to be like sort of like an off-brand Latin square. It's up to you, but yeah, thanks. Oh yeah, my partner's responsible for the lights as well. This is definitely not my doing, so they get full credit for this. It is very nice. I really feel like it's a big draw to the stream. Oh, any puns for box? Yeah, I don't know. This is also a bit of a lazy Sudoku. It's like Sudoku, but you don't have to do the part with the little squares inside. It's just lazy Sudoku, where you just have to get the rows and the columns. That's pretty much what it is. But algebraically, if you think about it this way, where the Latin square table is the multiplication table, you can ask about things like, well, what's a times a times a? And you can see, well, okay, it's a times a, because a times a is a, and that's a. And, if you look at this more, you can see that actually this is nothing but the group of order 3. So groups are special cases of Latin squares, or quasi-groups, but not all quasi-groups are groups. So there are many quasi-group. Most quasi-groups are not groups. But it's often helpful for theoretical reasons for us to think about these as actually like multiplication rules. And of course, you've already seen examples that make sense. Like, you probably do not want to see me write out the multiplication table for even this 8-element quaternion group, right? It'd be an 8x8 Latin square that I would have to write out. And of course, for the actual quaternion algebra, the multiplication would be an infinitely large table. It would still have the Latin square, kind of property. Okay, let's not do 0. Just leave out 0. But otherwise, it would have that Latin square property. But I wouldn't want to actually write that table out by hand. I'm not sure what you mean by class notes. Yeah, I'm not really sure. So what I was doing here was my goal is to try to improve the presentation of the main theorem in this paper, which is that every connected, orientable, triangulable, and manifold can be made by this construction. And now I'm talking about like what Latin squares are, and like kind of like the construction a little bit. To talk about like what the goal is. Oh yeah, I see. Yeah, they're just from earlier in the stream. I just gave the example, which is actually also one of the first examples from the paper, and so I just gave the example briefly. But yeah, so it's often helpful to think of the Latin square as being like thinking of it as a quasi-group, thinking of it as a multiplication. It's a lot less annoying to present them as algebraic rules. So actually, in this iteration, I'm not doing any algebraic topology, but hopefully, if I really stay up on my stuff, I will have some papers where I've computed some more algebraic topology kind of quantities from these things in the not too distant future. So I won't spoil it for you, but I have some calculations that I will post in the not too distant future. But at the moment, this is actually more like I wouldn't say it's necessarily algebraic topology. It does use algebra and there is topology, but I'm not computing the homology of anything currently. There's more to come. This has been a long consuming project, so there's definitely going to be more to come out of this in this one 80-page paper. So all right, well, in any case, So yeah, so are there any other questions, I guess, just about like Latin squares or quasi-groups? Those are like basically two sides of the same coin. One's just the more algebraic version, and one's like the combinatorics version. Or you can also ask me at some other time. So then the thing about partial Latin squares was that, you know, so a partial Latin square so it's very similar, but instead it's a table, maybe like here I'll give an example. Maybe, you know, it's a table perhaps something like this. You know, maybe like this, I don't know, whatever. And so the idea is that here, so here each symbol appears at most once in each row. So instead of exactly once, it's at most once, and each symbol, so each symbol also appears at most once in each column, and spots can be blank. So I didn't really emphasize this before, but back here I was kind of assuming that each of the spots in the square had to be filled in. That was kind of something that I would have stated explicitly if I was giving a formal definition, but that was kind of the idea. Here I'm allowing for spots in the partial Latin square to be blank. In other words, this is like an unsolved lazy Sudoku, where I only have to do the rows and columns. So so now that question that I was talking about before, this like Evans conjecture, and like there was this theorem from the 80s that had to do with when these puzzles were solvable, and by solvable, it was a little more to it than this, so I'm not going to get into like the full details of it, but basically it meant, can you fill this in to make a regular, like completed Latin square? And you're also optionally allowed to like add in some additional entries, like to make the table bigger. If you needed to add in a new symbol, that was allowed. So that's kind of the idea. So like for this one, assuming that I actually wrote it down correctly, actually we can see that it's completable because I just chose part of the table from up here, so you can definitely finish it. You know, so like if you wanted to complete it, you know, so maybe I'll just write like completing. If you wanted to complete it here, there might be more than one solution depending, but like here you can see that a lot of things are forced, and also that we don't have to add any more symbols to make it work. We can just say, well, you know, there's no C in the first row, but there's a C in the thing, so this probably should be C. Similarly, there's no B in this column here, the first column, so there should have to be a B somewhere, so it's there. And then, well, okay, here, there's no A in the last row, so there should be an A there. There's no C in this middle column, so that should be C. There's no A in the last column, so that should be A. And that's it. So it was possible to complete this Latin square, partial Latin square, to a complete one. But you know, it was natural to ask, if I just give you a random partial Latin square, can you finish it? And I'll even let you add, like, you know, only finitely many, you know, new symbols, but you can add like 1 million or 1 billion symbols if you need to finish one. It doesn't even have to be a limited number. Maybe one you need to add like 7 symbols for, the other one you need to add in like, you know, 1 million new rows and columns or whatever, but just can you finish it with some finite number of additional things? And the answer turned out to be yes. So the reason that that's good for us in this context is that I wanted to make this shape that was like, say, like these two triangles, and what I did was I did this elementary subdivision and then I said, if I had exactly these multiplications all being true, then I could make a partial Latin square where I fill in the spots for those multiplications, or like a partial quasi-group if you want to think of it that way, and then I just have to fill in the rest of the table to make a complete multiplication rule, and then I'll be done, and then I'll have some kind of quasi-group whose multiplication gives me this thing as part of its construction when we do the serenation construction that we described in our paper. So, of course, doing that in any particular example is a little bit tedious to actually like write out the details of it, because you choose your triangulation of like a torus, and then you subdivide it, and then you get all these multiplications, and then you get this partial Latin square, and then you fill out the rest of it to make a completed Latin square, and then that's your multiplication rule. We know that it can be done. I'm not going to sit here and write out an example for you because it's tedious, to actually do it by hand. But we know that it can be done, and so that means that that's why I have this yes here, because if I want to make some surface of whatever genus 3, 4, whatever, a million, then I know that I can find a triangulation of it. I can find a way to make this out of triangles. You just start adding triangles, and it is possible to find a way to triangulate all of these things, and then you make it out of triangles. You do that elementary subdivision that I described here. You get your partial Latin square. You solve the Sudoku thing for it, and then you have a completed one. That completed one is an algebraic structure, a quasi-group, to which you can apply our construction, and it will make the desired shape. So you can actually get every possible two-dimensional orientable surface, in other words, a donut with however many holes you want, by doing this construction. And so this is already one instance where, if you're someone who does non-associative algebraic structures, especially, things that are even less popular perhaps than Lie algebras or that kind of thing, if you're a quasi-group person, who really likes to think of them algebraically, then you're often trying to sell non-associativity to people who find it unsettling and don't want to deal with it, because people like their algebras to be associative, and so here's already one selling point. If we wanted to answer the same question for groups, we just don't know the answer. We just don't know if you can make a surface of any particular genus by using a group. We know some infinite list, that this isn't the real list, but just, I just chose some numbers. But we know some infinite list like this. There's certain numbers of holes that can be made, but we don't really need to know anything special. If we drop associativity, we can solve this problem in general. We can make any number of hole donut. Oh no, your advisor emailed you. Are you in trouble or something? Well, I hope that everything is going well. Oh yeah, it does mean that it can be done with finitely many triangles. So actually, it's always possible to give a finite triangulation of such a surface, and therefore you can make a finite partial Latin square or partial quasi-group. Where is it? Like the one that I had over here. And that means since you can complete it by adding at most finitely new symbols, that means you can do all of this with finitely many triangles, finitely many symbols, everything finite. Oh yeah, you should make sure to update your advisor. It's important to keep in touch with your advisor, even if your advisor is very chill. It's good to check in from time to time and keep them up to date on what's going on. So Well, it's still good, even if the update is that you didn't do anything. It's still good to say hi and just be like, oh, things have been really crazy because, like, you can also start a lot of professional development conversations by being like, oh, I didn't get anything done, but the reason was that I was really busy, like, organizing this other thing, or I went to a conference, or like. I don't know, like something, something else, and like, there's usually something to talk about, because like your advisor, to my mind anyway, your advisor should be advising you on, not just the actual mathematical content of your thesis, but also, also things related to, applying to jobs, doing outreach, like, getting ready to do more service things, assuming that you're going into academia, and, similar comments hold for industry, You can always say, I actually didn't make a lot of progress, but I worked on learning how to code some of the things we've been talking about, and so, like, that's going to be good for when I maybe transition into industry or whatever. There's always something to talk about. Or, depending on your relationship, you can always just talk about the latest, thing, video game or whatever it is that you're both into, Yeah, but anyway, so, okay, so everything that I just said, I want to be able to do that instead of for 2D shapes. I want to be able to do the 3, 4, or 100 whatever dimensional version of that. I want the higher dimensional version of everything that I just said. So I'm not going to, do all of, like, the whole like formal introduction to higher dimensional manifolds, but okay, you don't need that many triangles, right? Well, what does that many mean exactly? Like, you don't need like this many triangles, like when I subdivided. Oh, okay, you have no idea. Well, I mean, oh, Dobby, it's okay, buddy. It's okay. They know that you're here, I'm sure. I have no idea what he's. Are you good? Are you keeping us safe? All right. Okay. Well, yeah, I actually can't really quantify for you very well, I guess, anyway, how many... Well, no, wait, hold on. Okay, actually, I'm being silly. Let me think about this. So, I don't know in general if it's known how many triangles are the minimum amount that you need in order to make a surface of genus N. I know that specifically for the sphere, I know that you can do it with 4 triangles because it's a tetrahedron. So I know that you can view a sphere as something made with 4 triangles because it's that's like a sphere, triangulation of a sphere. But and I know that it is possible to have one of these triangulations for the torus that has, I don't know, like maybe like 17 triangles in it or something. I think that's the minimum that you can do. You can find an actual explicit reference for this in my senior thesis from when I was an undergrad, because I needed to actually use not just a number but a minimal triangulation of the torus to do something else, but it's related but not exactly this. Yeah, I mean, so anytime that you're going to be modeling some kind of surface on the computer, it can be helpful to represent it as a bunch of polygons or even a bunch of triangles, and using a minimum amount of them to get the whatever sort of precision or detail you want can be helpful. Of course, depending on your specific application, you might want to have like a finer mesh, and so that would kind of drive you to want to use more triangles. But yeah, or by this, when you said this would have engineering applications, do you mean like specifically the minimum triangulations, or just kind of this in general? I can definitely pitch some applications to you. if you're interested. But yeah, oh, this in general. Yeah, so I mean, yeah, because just like it depends on your context. It's both. It can perhaps be expensive. I think. I don't know for sure, but I would guess like in general, it's maybe not known what the minimum number of triangles needed to triangulate a given genus surface is. At least I don't remember ever seeing that this was like a well understood thing, but maybe I just haven't looked or haven't looked in the right place. But yeah, like sometimes it can be challenging to find a way to use less triangles. You know, it's probably not worth it in general. Often using more triangles can let you have a finer mesh that will let you approximate, smooth like real life things better. But as far as just like this general kind of construction, oh well, yeah. So if your goal is to just like topologically represent the surface, as in like you just want that these two things are homeomorphic to each other, like you can deform one into the other, the number of triangles only depends on the genus. So like it should be identical. Like if you don't care about anything to do with size and you just want to represent the shape of this thing, like from a topological perspective as opposed to a geometric one, just the number of holes is like there is a function that says if you have this many holes in your surface, this is the minimum number of triangles. The question is just that I don't think that we have a nice formula for computing what the values of that function are for larger numbers of holes. I'm actually pretty curious now though. I wonder if okay, I'm gonna actually try to look up the OEIS page on this because I'm so curious now. Let's see, minimum triangulation of surface. Let's see. Triangulations of sphere. I know. Okay. Only two things that are triangulations. Let's see. The number of rooted 2n face triangulations of an orientable surface of genus G. Number of combinatorially non-equivalent triangulations, quote unquote, of a compact surface that have only one vertex. Okay. Triangulated surfaces with n vertices. Order of minimal triangulation of the orientable. Okay, here we go. Okay. So this is the number, I think this is the minimum number of triangles or number of vertices, not the number of triangles, but okay, whatever. The number of vertices, the orientable closed surface of Sn, of genus N, that's the n-hole torus, that has the smallest number of vertices. Formula. Okay, never mind. There's an exact formula that's known. I just didn't know it before now. But there is an exact formula, which is the ceiling of 7 plus the square root of 1 plus 48 times the number of holes over 2, except for the number 2, it's 10. Just because that's what it is. Oh, I guess that means, because this is the number of vertices. I said 17 triangles, but that could be me remembering correctly. It's just, for whatever reason, I guess these people prefer to do it by the number of vertices. All right, that's great. So apparently this is known. Okay. So let's see. That's 2004. Okay, so that's in the graph. Okay, so the original. Okay, so the original papers must have been these. Yeah, I don't know if it's constructive, or I'm not really sure how they actually did it. I am curious though, so I think that I will maybe try to check out this paper at some point. I'm just gonna maybe, I'll just leave this up. I'm gonna look into this later. But okay, so there is an exact formula. Well, here, okay, this is a little bit of an aside, but since we're curious about this when we found it, I'll try to give a minimum I'll try to give a minimum number of elements in a quasi group that you do this construction for my paper to, and you get the desired surface of whatever genus. So apparently, here, maybe I'll move this over here so I can actually take a look at the formula and copy it over here for a second. So, all right. So now we've kind of gone off on an aside, but whatever. Let's see. So the claim is that the number of actual vertices that you need in a triangulation of the surface of genus N is a formula. The formula's I guess it's, say, A of N. Okay, so there's two cases. So the first case is when N is equal to 2, then it's 10. So that's when N is equal to 2. And then the remainder of this is claims here on OEIS that it is the ceiling of 7 plus the square root of 1 plus 48 times N over 2 okay. All right. And that's when N is not equal to 2. I love that there's just this one exception. There's just this one single exception that is, except the formula doesn't work when N equals 2. Let's just try it out for small values. It's just like a basic sort of sanity check. If I plug in 0, I get 7. The ceiling of 7 plus the square root of 1, so 8 over 2 is 4. I get 4. Okay, that looks good. I know that triangulation of the sphere. It's the one that's the tetrahedron. I know that makes sense. Okay, now this would be the number of triangles needed for the one-hole donut. That is the regular donut. Okay, so this is telling me it's the number of vertices. It happens that there's also 4 triangles here, but it's telling me the number of vertices. So if I plug in 1, I get 7 plus the square root of 49, so 14 over 2 is 7, or torus, yeah, that's right. It's the one-hole torus, the one-hole two-dimensional torus, or the genus 1 orientable compact, closed whatever surface. All right, so 14 over 2 is 7. Okay, so the claim is that 7 is oh yeah, right. Some people call this T2. It's kind of like, because like T1 is like the one-dimensional torus, which is the circle, and then T2 is the donut, but T2 is actually this, and then for higher dimensions, like the 3-dimensional version of the torus is T, or you could just think of it as T and not T1 cross T cross, and so on and so forth for the higher dimensional ones. So that's kind of why that's like that, I think. But yeah. Anyway, yeah, the circle is the one-dimensional donut. Yeah, so anyway, I can't really draw the triangulation here, but the claim is that there's a triangulation of the two-dimensional torus with 7 vertices, and so like we'll buy this, I guess. I'll just say we'll buy this. Oh, if I can spell buy, that would be good. Okay, we'll buy this. And now, apparently A of 2 equals 10, so apparently you need 10 vertices in order to do the 2-hole donut. The one that kind of looks like a dumbbell. Let's actually look at what this formula gives us. So if I do 48 times 2, so I'll get 96. Okay, so I need the ceiling of 7 plus the square root of 97 divided by 2. All right, well, let's see. If I square 10, I get 100. If I square 9, I get 81. So this is like, you know. Wait, how much does? Oh yeah, we'll buy. Yeah. How much does it cost? How much does it cost to buy this particular fact about the torus? Well, one way of quantifying it is how much does the computing resources to actually produce such a minimal triangulation cost you. And I would guess it's basically next to nothing, because this is probably a very, very cheap thing to do by sheer brute force on a modern computer. But okay, so this is this ceiling. Okay, so at the ceiling of this. So let's see, just for just for fun, right? So this is smaller than 7 plus the square root of 100. So 17 over 2, and on the other side, if I do 9 squared, so 7 plus 9 is 16 over 2. Okay, so this is then if it's between 8 and 8.5, then it's got to be that well, it's definitely not equal to 8, so the ceiling has to be 9, but 9 is not equal to 10. I'm really curious now. I'm not going to actually produce the paper that I found the citation from OEIS on, but like, what is going on with this thing that it only doesn't work when you plug in the number 2 and you get 9 instead of 10? How do they know that that's the only exception, and for every other genus this is the correct formula? That's just I mean, it's possible it's a mistake, first of all. It's not like no one's ever made a mistake on any of these encyclopedias. Like, one thing I can think is that there is a triangulation that uses this many vertices, but that they don't know that it's minimal, and there was just something lost in translation. If they actually truly know that this is a formula for the minimum number of vertices that you could ever use, then I'm really curious how this formula is correct for everything except for when the genus is 2. Yeah, like, what is going on with the genus 2 torus that means that you can't, because like whatever general theoretical argument they have, it means that argument would indicate that 9, it should be 9 vertices, but you can only do 10. If it's the fact that 2 is the only even prime, this is further evidence that 2 is not a prime. Yeah, I truly have no idea here. I'm really not sure, honestly, what they were up to. I guess one indication would be what kinds of journals these were published in. Let's see. No, I don't think there's anything like especially indicative of what the methods were. There's also no indication of exactly which references were used for which thing. There's an older one that's in German, but it's not really clear whether the formula was produced back in 1955, in which case homological methods are possible but less likely, versus 1980. Yeah, I don't know. At the moment, I don't know. But it seems like at least it's halfway reasonable to believe that this formula is correct. Okay, so this is the formula. And now, just because, just to make our lives easier, let's just assume that n is greater than 3 or greater than 2, whatever. Let's assume that n is greater than 2, just so that my life is easier. So, okay, so then, no, I'm not going to be able to give you an exact number. I'm only going to be able to give you a bound. Unless I can find another sequence in OEIS, which is the actual number of triangles. I need the number of triangles to figure out how many vertices I add when I do the elementary subdivision. Just knowing the number of vertices isn't sufficient. So let's see. Okay. If I had just read the bottom of the page, no, thank you. I don't need a translation. If I had just read the bottom of the page, number of triangles. Oh, I thought 17, but it looks like genus 1 is 14. I was close. Okay, this is the actual thing that I want. Oh, okay, and there's a formula here as well. All right, this is what I want. The number of, actually I want both of them. I really need both of them. So let me just copy the appropriate formulas over here so that I can reference them as I do this. I'm gonna try to give you a lower bound. So for the number of vertices in a minimal triangulation, I'm going to call that V of n, and that's going to be given by the good part of the formula, which is the ceiling of 7 plus the square root of 1 plus 48 times the genus divided by 2. All right, that's the number of vertices. The number of triangles, I'll call T of n. And that's going to be apparently 2 times, let me make sure I have my parentheses correct. It's that. All right. And there's an exception for the 2 case there as well. Okay, so it's going to be 2 times the ceiling of this. Same quantity, which I am curious where it comes from, and then plus 4 times n minus 1. Oh yeah. Yeah, things are good. Things are good when I like them. Yeah. So okay. So here's our 2 formulas that we have apparently. All right. And so okay. And so the okay. So the number of elements in our partial Latin square. Okay, actually, I wanna just pause for a second. In case you noticed, I do this sometimes. I've started doing this as I've gotten older, and I'm glad that I've captured it live. I did it at least once earlier in the stream as well. If you notice, I started writing AT, like to write the last part of the word Latin, and then I returned to write the letter L. The older I get, the more frequently I actually start writing words in the middle of the word and then return to finish the beginning of the word later. It's not something I've consciously decided to do, and as far as I know, it's not like indicative of any kind of neurological problem or anything. I've just been doing that. I don't really know why, but that's a thing that I do. Anyway, just keep an eye on that. I don't know. I don't know. The number of elements in our partial Latin square for making the genus n surface. Oh, thanks. Yeah. It's harder when I can't actually see what you're typing to tell that you wrote the W last. So that's going to be, well, we're going to have each of the vertices that we started out with, but we're going to add 1 vertex for each triangle because that's what you do when you do the elementary subdivision. Therefore, we're going to add 1 copy of this to this thing, and so the number of vertices, the number of elements in our partial Latin square for genus n is going to be, well, it's going to be 3 times the ceiling of 7 plus the square root of 1 plus 48 times n divided by 2 plus 4 times n minus 1. Okay? So now that's not exactly the amount of elements of the corresponding quasi-group, and there may be more than one, by the way, just to mention. Sometimes Sudoku puzzles have more than one solution. There might be more than one way to complete a partial Latin square into a completed one. So there might even possibly be two different ways of completing a partial Latin square into a completed one that is the minimal size. So like, it's not necessarily the answer, but there is an answer to the problem. But it might have more vertices than this. It might have more elements than this, I guess I should say. So the question is how many more? And now let me double check the statement of that theorem that I used, and I'll actually give you the quantitative version of it, which I don't know if I mentioned it in the preprint or the draft that I have right now. So I'll just look it up on Wikipedia. Or whatever. I guess there's no Wikipedia page. That's fine. Let's just look at these notes. This seems good. Thank you. Okay, so any n by n. Oh, I didn't spell it right. Sorry, I misspelled Smetyanek. I always misspell and pronounce it. I apparently can't spell it yet, but that's fine. This theorem from 1981, I couldn't remember it was 81, but I did remember it was the 80s. Any n by n partial Latin square with at most n minus 1 entries can be completed to a Latin square. Okay. Well, what is that? How do we flip that around? Well, we have a partial Latin square that has this many elements, like it has this many rows and columns, right? But we have to figure out how many actual entries are filled inside of this thing. And so, well, the number of entries, and because if it has too many entries, we'll have to add more rows to be able to solve the puzzle, or more rows and columns. The number of entries is the number of multiplications that I have to enforce. But if you think about it, we're gonna get 3 multiplications for each triangle, right? Because like if I start off with a triangle and I do the elementary subdivision, then I'm gonna get 3 multiplications. Before, like how I had I had like a times b was the new element x, b times c was the new element x, c times a was the new element x. So I have 3 spots filled in for each triangle. So this is 3 times the number of triangles. Well, okay. What's the number of triangles? It's that. So, okay. So actually, one way to say this is it's just 3 times t of n. But the number of actual elements that I have, so that's the number of entries. But the number of elements that I have, the number of rows and columns, well, that's actually equal to how do I want to say this? Well, it's equal to v of n plus t of n, but I kind of want it to just be in terms of t of n. So let's see. V of n, okay, I'll say it this way. So it's v of n plus t of n, but v of n is actually the same thing as if I took t of n, subtracted 4 times n minus 1, and divided by 2. So okay, so plus t of n. Okay, so in other words, so here we're going to have 1/2 t of n. Here we're going to have 1. So 3/2 times the number of triangles minus 2 times n minus 1. Okay, so if I have this many entries, then according to Smetyanik's theorem, or if one day I'll learn how to pronounce it properly, so if I have 3 times t of n entries, the number of rows and columns in such a partial quasi-group, partial Latin square, so that I could solve them, well, if the number of entries is n minus 1, I need it to be n by n. So in other words, if the number of entries was k, I need it to be k plus 1 by k plus 1. So if I have this many entries, I need 3 times t of n plus 1 rows and columns to guarantee, to solve, I guess I'll say, to complete the partial Latin square. Okay, and so maybe not shockingly, well, the number of elements that I actually would end up with in my partial, the number of elements that I would end up with here, the number of rows and columns, it's a little bit, it's like somewhat less than 3/2 times t of n. So actually, it's like half of what we need. So we definitely do have to add entries, and therefore it looks like actually this is the minimum number that is necessary in general according to that theorem. Now in reality, for this particular case, it may be smaller, but the end result is like a corollary of all of this. The end result is that here, maybe I'll even call it a corollary. Look, we actually proved something today. That's nice. There is there's a quasi-group Q of order, let's see, what did I say? 3 times t of n plus 1. Oh, okay, I see. All right. Yay, we proved something. 3 times t of n plus 1. Okay. So there is a quasi-group Q of order 6 times the ceiling of 7 plus the square root of 1 plus 48n divided by 2, and then let's see, what did we have for t of n? Plus 4n minus 1, so I'm going to split that, I'm going to distribute plus 4n minus 4. Okay, but then I have to multiply by 3, so plus 12n minus 12, but then plus 1, so minus 11. Okay. Such that if we apply our construction to that quasi-group, contains, or well, I'll just say has, a surface of genus n as one of its connected components. Okay, so yeah, I mean, assuming there haven't been any arithmetic mistakes or other errors in reasoning, it seems at the moment that we have the following corollary, which is that there is some quasi-group which has, or in other words, a Latin square, if you think of it as a multiplication, where it has 6 times the ceiling of 7 plus the square root of 1 plus 48n over 2 plus 12n minus 11. It has that many rows and columns, or it has that many elements. I almost forgot to say this is for n is not equal to 2. Yeah, I mean, it probably works with n equal to, I mean, yeah, it should work for it should work for n equals 0 and 1 as well, but yeah, okay, fine. For n not equal to 2, there is a quasi-group of this order which has, when you do this serenation process, when you make the shape out of it, that it has that surface of genus n as one of its connected components. So we can actually quantify how many vertices we need in order to make this occur. Now, it's possible that you can do better than this, as in this is not necessarily the minimum amount, because I used a theorem that was about completing partial Latin squares in general, but these ones might turn out to be more special and might turn out to actually be solvable using less new entries. I don't know the actual minimum amount of elements needed, but this is a this is an upper bound on how many of those elements are needed. So you can always, you never have to take more than this many. And so now it's also worth thinking about if you think about it asymptotically, as n grows very large, what's going to happen? Well, this term is basically the square root of n. I mean, if you do away with the constants, this whole first term is basically the square root of n, just like not anything compared to n. So really, like, this grows about with the order. You basically need to add at least like, okay, well, one way to say this is that you have to add about a dozen new elements for every new hole that you add to the many-holed torus. It grows about as quickly as the number of holes that you choose. It's just by like a factor of 12. So like pretty much every time you add a new hole, you add 12 new elements, and you can do it. Like that's pretty much the thing. Now, how to actually do that constructively is a different question, and it might be better answered by actually looking at the original proof of these quantities, if it's constructive. Yeah, at the moment I can only tell you that this thing exists, but I can't actually describe its algebraic structure in any more detail. But there are such things. It's actually not too bad either. Like having growth that's like the order of n, like that's not bad at all. So like just as a quick check, or maybe not check, but just to like check it out a little bit, like what the result is saying. That means that if we take like n equals 3, what is this telling us? The n equals 3 case is telling us that if I do if I take okay, actually I'm tired of showing off doing the basic estimates like manually, so I'm just gonna actually just do some values in the calculator just to give us an idea of what's going on here. So let's just do I'm just gonna write this in the in Sage really quick. Let's see, 7 plus the square root of 1 plus 48 times the genus. Oh, and all that's over 2. Oh, I said floor, but it's ceiling. Oh, okay. You already got 85. I'm typing out the general function here, times plus 12 times n minus 11. Oh. Okay, so all right. So hopefully I typed it out correctly. Let's see. Yeah, 85. Okay. All right. So I was just being I was just being shy, but here's what I just typed out. Just in case I made a mistake, I was just being shy, but this is fine. Yeah, so it looks like we have 85 elements for the three-hole donut. 103 elements will do you for the four-hole donut. 121. Well, yeah. So I mean, that's actually pretty reasonable if you think about it. I mean, like it's still like it's not a tiny algebraic structure, but yeah, a three-hole donut, like apparently it's possible to study that by studying an 85 element Latin square or quasigroup. Yeah, so I don't know what that I don't know what such an 85 element quasigroup actually looks like in any more detail than it has to be compatible with such a triangulation, but there is out there, you know, some 85 element, there is some 85 element quasigroup, I claim, who, when you do this construction to it, one of the pieces that you get out is a three-hole donut. And so this state of affairs is significantly better than the one for groups in the sense that we actually can know that we can do this for every possible one of these surfaces. So that wasn't the number of holes. That was the number of elements that you would need in the quasigroup that makes the surface with just three holes. So for the 85-hole donut, if we wanted 85 holes in the donut, which I agree probably wouldn't sell as well, we would need 1,225 elements in our quasigroup according to this. Oh, and I guess I keep saying things like, oh, the 100-hole donut, but let's just see, 1,423. All right, so yeah, it is actually possible by studying an algebraic structure with only, 1,000 some odd elements to study the, to study, like, perhaps combinatorially the surface of genus 100. And so that's actually a lot better than I expected, honestly. I kind of thought that it would be way bigger. I also didn't realize, as I told you before starting the stream, that actually there were formula, at least according to OEIS, there were formulas that claimed to be the minimum number. I'm pretty sure it said the minimum that was possible, not just the minimum known. Yeah, of course, it depends on what scale you use. The people the people who use topological data analysis, as we've talked about a little bit before on this stream, you've got to think about all the different possible scales, and you get different numbers of holes depending on what scale you use. From very far away, Earth just looks like a little point. I mean, it doesn't even look like it has any holes in it at all. I'm trying to. It's already extremely well done by mathematicians, but I'm gonna try to corner my own piece of the many-hole donut market in the 21st century here. I'm really wondering. Okay, I just want to super double check now. It says minimal. So the claim here is that this is the smallest possible number. Like that these are. It's not just the smallest known. It's the smallest possible. I almost wonder if I've actually cited this paper before, and that's where I got the minimal triangulation with 14 triangles from, and I just forgot about it and forgot the other details of this because it's been a while since my senior thesis. Wow, it's actually been 7 years. It's 5 years of grad school and 2 years of my first postdoc. It's been 7 years. Where does the time go? Anyway, it seems good. I am curious to find the actual quasigroup now. That is the one that gives you the three-hole donut, or see if there's more than one. But I don't think I have a utility set up that solves this. That's just readily available. I don't think Sage does it just automatically. I think that there's more work involved, perhaps. I actually don't know if they're good algorithms in general. Just knowing that it's possible, I'm not sure. Because I actually don't know the proof off the top of my head. I just know that it's possible, right? because the reason I became interested in this result was precisely for this reason. Like this is why I know it, and so I feel like it's a proof that I should know, but I don't. So I'd have to see if it's constructive, and if it was, then that would maybe give me an algorithm, and I could see if it's fast and try to produce an example. But I think maybe it's not reasonable to try to do that within the next hour. I don't know. I did go off from what I originally planned to do today, but that's fine. This is still on the theme of what I wanted to talk about, and I actually computed something that I've never computed before, which was cool. What do people think? Do people have any other questions, I guess, at this point, or anything of that nature? Well, I feel good about this. Seems like a good thing. Yeah, I don't really know of any particular use for these numbers, but it seems reasonable. No, I do know of one other consequence. All right, so I can't tell you whether your advisor is disappointed in you. Any relationship between your advisor's behavior and their opinion of you has to, pass through your perception, and it depends on each of your individual personalities and so forth. And I can't answer that. I mostly know about math things and computer things, and there is a certain social element to being a mathematician or being some kind of internet personality or whatever. But I'm not qualified to diagnose the nature of your relationship with your advisor. Oh yeah, you could ask. That is possible. It doesn't mean that you'll get a true answer, but you can ask. Okay, I did realize something else. Oh, you're trying to read I'm sorry. I was thinking of Bertrand Russell. Okay, Newton's Principia. I've never really tried to read. I mean, at that point, there's a language. There's a bit of a language difference, isn't there? It's not just notation, but you should be familiar with mathematical literature at the time in order to read it properly, right? Yeah. Sometimes people joke when they really mean to say something. But it doesn't mean that maybe he'd be super disappointed, but it would be good. But life happens, and something I'll tell I'll tell students, grad students, whatever, is that obviously, hopefully, with any luck, your advisor, your professor, whoever cares about your progress and wants you to do well. But we've all had a bunch of students. We've all seen all sorts of different things. We know that life happens, and the reality is that we're judging you usually way less than you think that you're being judged. It's just the reality is that your experience of a class, of doing a project with an advisor, it's all about you because it's your experience. That's natural, But okay, well, you're a little bit more in the spotlight then, but still, he's probably got other classes, he's got other projects, other collaborators, and generally speaking, we all have better things to do with our time than deeply agonize over what's going on with each student. So when a student apologizes profusely and says, oh, I really need an extension, whatever, unless something else has already been going on or it's been too many times or whatever, people usually, the very first time, they're oh, I feel so guilty, and I'm just I understand that life happens, people get sick, there are accidents, I care, but I'm not judging you. I'm not judging you that harshly because I have better things to do with my time than sit around and judge people all day. I just want you to have a good time and do good in the class or on the project or whatever, just do your best, Now, maybe not everyone feels that way. There are people who are really, a lot more intense, I think, than I am. But it's that's what it is. I mean, that's my perspective, anyways. Like, we're not really judging you that harshly. I mean, that doesn't mean you should just do whatever you want and expect it to be fine. But you don't need to worry quite that much, I think. Yeah, but okay. I realized something. Oh, well, again, it's your unique situation. I can't tell you for sure whether you doing whatever you want is actually the right thing or not. If you're doing good things and you do whatever you want and your advisor's cool and everything's cool, then it's great. But depending on what whatever you want consists of, it may or may not work out for you. Yeah, but best of luck to you. It's always the dream is to do whatever you want. That's the, that would be nice. Okay, so here's what I realized. 85 is not a prime number. So it's divisible by 5. Probably some other stuff too. So if there was an n for which the number of elements was prime, we'd be able to say something a little bit more. Yeah, getting your thesis done sounds like a thing that your advisor will probably support. If that's whatever you want to do is to do that, then probably you will be well supported in that endeavor. So I don't actually want to go through this and manually check to see if each of these is a prime. So let me see if I can just get one. How do I want to say this? So I guess let's just give it a bound. Let's just do 2 to 1,000. If I think is prime is the function. Okay, well actually let me just check first. Okay, that's the correct function. Okay. So for n from there, so if f of n is prime, print n f of n well, I'll just make it a tuple. Okay. So I think, unless I'm mistaken, somewhere in the course of this calculation, the answer is that there are many numbers for which the number is prime. Oh, 103. I don't know that I have the primes memorized that much, but I may have been able to guess that 103 was prime. But all right. So 4 holes, 7 holes, 9, 10, 11, 12. Wow, actually a lot of these are prime. Huh. It's kind of surprising, right? Like, I guess the question is, what does the density of it look like? Like, are there still this many primes, like, going forward, or am I just seeing the small numbers giving me a surprising behavior because there aren't that many numbers that are, below 100 or whatever? Well, in any case, for all of these different genuses, 4-hole donut, 7-hole donut, 9-hole donut, 10, 11, 12, 13, 15, 19, 22, 26, and so forth, all of these are giving me a prime number of elements, at least that are the result of using Smetaniak's theorem. sorry, I still don't know how to pronounce it correctly, to get an upper bound on how many elements are needed in a quasi-group that does this. And so because there is a quasi-group that works for this, that is of these orders, that means it's a quasi-group of prime order. But here I can get into the description a little more if you would like. But for those of you familiar with, say, groups and simple groups, you know that if you have a normal subgroup, the order of the normal subgroup should divide the order of the group. So if you're going to have any normal subgroups and the group has a prime number of elements, well, there aren't very many possibilities. It's either got to be the whole group or it's got to be the trivial subgroup that has one element. So now, quasi-groups don't quite have this notion of like a normal sub-quasi-group. If there's an identity element, and then they do, but like in general they don't have to. But still, there's a similar thing here where there should be this like regular partition of the quasi-group into pieces in order of the same size, in order for there to be a quotient, in order for it to have like what is like a quotient of a group. So the fact that all of these are prime means that there's actually that there should actually be a simple quasi-group, one that has no proper non-trivial quotients. That's like sort of basic in some way algebraically, that there are simple ones that give you each of the desired shapes. And that's, it's not necessarily the most shocking thing in the world, because like there's lots of simple quasi-groups, like it's it's a thing. There's a whole bunch of them out there. But I was just thinking, just for whatever reason, my initial guess was that the examples would tend to be of composite order, and so these things would have, would have these quotients. They would have what's called non-trivial proper congruences. But it looks like for a lot of numbers of wholes, like starting with 4, and there's a whole bunch of them, it doesn't seem to be the case, actually. So algebraically, they're kind of indivisible. They're kind of like the atomic sort of, simple pieces that other things are made from. And that's pretty interesting. Like that's not maybe totally obvious. Now again, this doesn't guarantee that these are the minimal order quasi-groups that make these donuts with whatever number of holes, but at least like there is one that does it. And the fact that they're simple actually makes them maybe kind of even more interesting than if there was a smaller example, just because, well, there's a simple example. And so like, I think that's pretty interesting. Because like, being able to just say like, I can make this algebraic structure, this Latin square, whatever, that represents like that encodes the 3-hole donut that has 85 elements, like it's already kind of interesting, because then you can say, well, instead of, studying this either by hand or in the computer or whatever, instead of studying this, I just have some table that has 85 entries that is, I can just study this thing instead, whatever the case may be here. But what's even more interesting is like in the n = 4 case, for instance, where we have 103 elements, because this is a prime number, because that's a prime number, that means that if we wanted to understand the 4-hole donut and we wanted to do it algebraically, it actually tells us a little bit more about the resulting algebraic structure from the construction that I described. If we wanted a 4-hole donut like this, then there would be such an algebraic structure. So over here, we would actually have a simple 103 element quasi-group. And so that basically means like there's no proper non-trivial quotients, like like this is sort of a basic building block for other quasi-groups, similar to how the prime numbers are basic building blocks for numbers. So quasi-groups don't have to have prime order in order to be simple. Like there can be simple quasi-groups that do not have prime order, but it is forced. It is forced in this case, and so I think that's pretty interesting, because that means that it's likely that a lot of the time when you have one of these algebraic structures that's a basic building block, that's simple, or in universal algebra there's a slightly more general condition that's kind of the correct one, which is what's called being subdirectly irreducible. But when this happens, usually the things that have this property are they're well, okay, I don't want to just say simple, but they somehow are they can be described in terms of other things usually, but they're kind of in some sense, like there's something that can be difficult to describe in terms of anything else other than themselves, and they're the things that you kind of want to use to build everything else. So like, for instance, a big project in the 20th century was the classification of finite simple groups, and this is basically a non-associative analog of the same type of object. This is a finite simple quasi-group instead. So like the finite simple groups, but just non-associative. And there are way more of these. There's probably no real hope that we can actually classify the finite simple quasi-groups. It just seems like it would be harder. There's no guarantee. I mean, it could turn out that the associative part of it is the hard part, and the rest of it's pretty easy. I don't know. I've never actually really seriously tried or even looked at the literature on like an attempt at classification, if it exists. Yeah, I mean, it's probably hopeless. But that's okay. We still have this, and yeah. So like, I can't say for sure. Like, of course, it's possible that it's possible that the algebra of whatever this 103 element quasi-group is, like, wouldn't be. Oh yeah, there are different lands to conquer. Yeah, there's, well, if we did the finite simple groups, and hopefully some people will actually be able to digest the shortened proof. I'm not really looking to embark on being able to actually reproduce any sizable amount of the proof of the classification theorem, but there are people trying to reduce it to a more digestible size. And if you are really into group theory, that specifically, then more power to you. And they're getting it down to, I think the goal is less than 10 or 20,000 pages for the new one. I don't really keep up on it super much, but it's still going. They're trying to condense it and fill in the gaps and stuff. I think formal verification is a long ways away, probably, but I think people have done fight Thompson and formal theorem proving systems, but yeah, it's going to be a long process. Hopefully by 2100 we'll have some kind of formal verification of the classification. But yeah, as for quasi groups, I don't know if it's really. I'm not sure whether or not it's a reasonable thing to embark on, but it's a thing that exists. But yeah, I mean, a simpler goal might just be to find an example of such a 103 element quasi-group that can be used to make this this torus. Natural things to ask might be like, okay, the triangulation of the four-hole donut that you get. Sorry, I said torus, but this is a genus 4 surface, not a torus. The four-hole donut that you get, the genus 4 surface. Oh, the Badgers will have taken over mathematics. Why Badgers specifically? Well, so we'll see we'll see if we come up with an answer to that one. But oh, didn't someone use was it Spivak? Somebody used badgers to, oh, because one attacked you recently. So I hope you're okay. You know, I've heard that the honey badger in particular is a tenacious creature. You know, oh, they're getting more and more powerful. Yeah, if you don't know about the honey badger, you should look it up. There's some really informative documentaries out there about its various activities and lifestyle. It's incredible. It's really quite something. Yeah, just really wondrous creatures. But yeah, oh, you're a honey badger. Now, am I the only person old enough to know what I'm talking about right now, or are other people familiar with the honey badger? Is that still a thing? Oh, allegedly. Well, in any case, if you do some research, you can find out about this ancient piece of internet history. Yeah, the meme, the video, the legend. It's honey badger, you know. But yeah, I mean, if they do take over math, I hope that they bring their tenacity to it, you know. Oh, okay, just barely old enough. All right. Yeah, this is more of a millennial thing. I can only speak Zoomer a little bit, so yeah. If you get online early enough, then you'll know. Then you know the old people things or whatever. Yeah. Yeah, no, I am in fact a millennial, if you can believe it. But yeah, so I would like to actually. Okay, I can't handle. I'm sorry, I can't handle something called Meme Center. I think that's where I have to call it. I'm gonna tap out. I don't think I'm prepared for that. Yeah, I'm sure it was terrible. I'm sure it was just awful. Yeah, no, that was the cultural singularity, you know, when memes became a meme, it was all downhill from there. There was no stopping it after that point. But on the topic of quasi, okay, we're just going down memory lane now. Yeah, Pop Tropica was after my time, I believe. But okay. Oh, okay. So you guys are more on the same level there as far as like the, yeah. I think Pop Tropica was a little bit after me. But yeah. So if okay, so here's what I want to do now. This is now my goal. I don't know if I'll accomplish it during the stream, but this is now my goal. I want to construct a 103 element quasi group that can be used to make the 4-hole donut, and I'm going to try to figure out how many vertices there are in the triangulation of the 4-hole donut that comes from this thing. And I'm going to try to figure out if it's a minimal. Oh, no. I know that it's a minimal triangulation because that's how I made it. Never mind. So it will be a minimal triangulation. Okay. Never mind. I'm good. Oh, okay, yeah. So, see, I didn't even know there were islands. I have no idea, like, what is, I have no idea what the deal with this. I assume it was like a website where you went on some kind of adventure or something. Like it was a game on the internet, maybe. That's what I'm gonna assume. That's my guess for that one. Yeah. No, I remember playing games that were made with it was Macromedia Flash. So Adobe bought it at some point, I think, but it was Macromedia Flash, and people would make games and little animations that were interactive and stuff. And then later it was decided that things being interactive on the internet was not the direction that we wanted to go in as a society, and so everything was sort of remade in this perspective where like there's one person or entity or business or whatever that is like really, controlling the interaction and distributing information to you, and you just consume it like it's television. Still we have chat, like there's the chat, and like that's good or whatever, and I suppose it would be really confusing if there were just like a bunch of people screaming over each other about different topics or whatever, so like that's reasonable. But anyway, I'm just kind of complaining about how I feel like things have become much more walled in as Facebook and Google and everyone have really, tried to corral everyone into their systems. YouTube actually used to warn you that you should not share your personal information, but in order for me to be able to use all of the features of YouTube, I now have to supply a government-issued ID to them. So YouTube is actually, now under Google, YouTube is actually engaging in precisely the behavior that it previously warned us dangerous people would do when running a website. And so that's the world that we live in now. Let's see. Oh, okay. Oh, you could steal. Okay, but they would still have their outfit, right? Like you wouldn't actually take it away from them, but you could see, that's nice. I think that's nice. That sounds perfectly pleasant, good for kids. You can just explore the various worlds, and people have little outfits and everything. Yeah. Yeah, you just copy the outfit. Yeah, that's great. I think that's fantastic. It's wholesome. All right, so I've convinced myself that I can make these things. I need a computer program that will actually make them for me. But so one of the first things that you usually study about algebraic structures like this is their quotients, their congruences. But if these things are simple, as a lot of them are, then they don't have any of those, so that's not available to study. So a next question would be, what about maybe sub-algebras, like sub-quasi-groups? And because I don't have any better understanding of what this 103 element thing would look like, I'm going to have to use the computer if I want to experiment at first, because I can't do this by hand. It would take forever. It's too tedious. So I'm going to have to use the computer to do this, and then I'm going to have to see if I can find any sub-quasi-groups, some subsets that are closed under the operations. I'm thinking that if I do, I'm mostly going to get things. I'm going to get one that's pretty big that includes... Actually, I'm really not sure. There's so many aspects to this, I'm really not sure what... as far as the construction, I'm really not sure what it's going to end up looking like. I know that it'll have this thing inside of it, but it's actually pretty exciting because I'm really not sure what will come out of it. But yeah, sub-algebras, sub-quasi-groups... I know that the quotient situation isn't very interesting for most of these. And then I guess identities, see if there's any formulas that this thing satisfies, which I don't really know how I'm realistically going to start looking for those, because this thing is going to be... It has no obvious structure that I can understand. But I think I will try to do some computational examples of this, because I'm really curious. Now that I know these are simple, if they had all been composite order, I would have been whatever. But the fact that so many of them are prime, I'm now really curious, because it's just so many of them give you a prime number of elements that I'm what is going on with all these things? It really might not be anything particularly exciting or anything I can really say too much about, but I hope it's something interesting. Now you also might wonder why do I care about this, aside from the fact that I can do this, right? Why do I care about representing this shape, which is a perfectly good shape that I can draw as a blob on here, as one of these giant Latin squares? And well, you know, one one reason that it might be interesting, you know, is that this is you know, this is somehow a representation of this shape that is something we can like compute with. Like it's something that's algebraic, and so you know, understanding that algebra can maybe help us to understand the shape. And you might say, well, okay, we understand the two-dimensional shapes like really well. We understand these donuts really well, or you know, many-hole donuts or whatever. But the idea is, I want to do the same type of thing in 3 dimensions or above. And so there, you know, we might not have a nice list of what all of the analogs of these guys are that are 3 or 4 or 100,000 dimensional, but we can understand the corresponding kinds of algebraic structures that are like Latin squares. They're not Latin squares, but they're like Latin squares. And the idea would be then we could use our understanding of those to understand the shapes. And so this is kind of a good testing ground for that, especially because if I could understand like any better relationship between the algebra of this and the fact that it has the shape inside of it, besides just the way I literally constructed it, then that would be really good. I think I'm going to need to do some of this on the computer, like actually have the computer do some of this in order to start experimenting with it, because I can't do this by hand. Well, are there any other questions at this point, or any other things? Is it called Sage because it helps you to do things that you can't really do by hand? I actually don't know why they called it Sage originally. I think it was originally officially Sage Math, I believe. Like, I think it was like either like this, or maybe Sage was all capitalized, but at some point they just dropped the math and they just called it Sage. Yeah, it's a wise master. Yeah. Yeah. You know, like Sage has been a really good thing for me. It's yeah, let's come up with backronyms for Sage. Sage has been a really good thing for me. It definitely still doesn't do everything I'd like for it to, but that's why it's open source and people can keep adding to it. If I had more time in my life, I would definitely contribute to Sage. Maybe I will at some point, because I'll discover that instead of just writing things using Sage, some of them would actually be better to just contribute as additions to the project. But I'm not really familiar with the organization of it as far as like actually developing for it. I've never done it. But it is open source, and so in theory it should be possible for you to make something and say, you know, I think this would be a good addition, maybe get it added. But yeah, I should definitely try coding some of this. Actually, I will mention, you know, I actually have written, I'm sure it looks like really primitive now compared to what I would write today if I tried to do the same thing again, but I've written some stuff for Sage that's probably way out of date now too, but I've written some stuff for doing universal algebra things in Sage, which is a bit relevant, and maybe I'll actually refresh it if I decide to do some more of this stuff computationally, just to see some examples. Let me see if I can actually find the project here. Oh, this is gonna be a trip down memory lane here. Okay, this is gonna be so old. I did this many years ago. All right, so here we are. So this is actually before this whole paper and project and everything, when I was just thinking about sort of a more simplistic way of viewing algebraic structures as simplicial complexes. 8 years ago. Oh, that was so long ago. Wow. I'm really impressed to have an 11-year-old on the stream here. Generation Alpha is really getting to it with the with the you know, perusing math on the internet. I actually, you know, now I feel like I should know the rules. Are you allowed to claim to be 11 years old on my stream? Do I have to kick you out for that reason? I'm not sure. This isn't really, you know, I mean, it's something that only adults would probably be interested in, maybe, but like I don't think that this is really something that, you know, I don't know. There's like rules about like if you're 13 years old, if you're under 13 years old, I think you're not supposed to be on certain social media sites or something like that. Oh, it is technically illegal. All right. Well, because I don't actually know the details, and you may be joking, I think I'll just leave it for now. But I feel like this is something I should look up. And oh, I see. Well, I don't know if illegal is the proper term. It might be a violation of the terms of service. But yeah, I'm gonna go with that you were joking and that you're 25 years old. I think that's a lot more plausible. But yeah. All right. Let's see. So 8 years ago, I made whatever this is. Oh, this is just a copy of the GPL here. All right, that's nice. Is that what my README file is? Okay. This thing really should have a README. All right. So anyway, let's see what we have here. Oh, this is when I was an undergrad. Let's see. So, what is this? Is this really necessary that this is a function? I guess. All right. Let's see. This is my class for what an algebraic structure is. You can view these things as matrices, finite fields. Various things from Sage can be cast to being algebraic structures. What I really need to do is go into Sage, the Sage like documentation, and look at like how algebraic structures in general are actually treated. See what that looks like. You know, one of the big things is that there is this universal algebra calculator. Here, let me actually try to find it. So there's this calculator. That is good for doing like, you know, studying a lot of these different things that you'd like to know about algebraic structures in the universal algebra sense. Let's see. Okay, I found the website. Okay, so back in the day, Ralph Fries wrote the universal algebra calculator in Java. And, you know, I mean, it's Java, it's object-oriented, you know, there's some gap compatibility, you know, you can use it to, like, you know, study various kinds of algebraic structures. But the thing is, like, there's a lot of people who would like to use this kind of functionality and all of these various algorithms that have been implemented in this thing that are done very efficiently and everything, and, you know, have an interface that's in Python, or, you know, maybe Haskell or something that's, you know, something that's not Java. And so, like, I'm not the only person who's written like some kind of interface for this. Like, this is like something that like people keep doing. And I kind of like a more modern analog of the universal algebra calculator, maybe something like that to be implemented like within Sage or something like that. It's kind of a bigger thing to do. It's not something that's like just going to be like a one-off, you know, a one-off project. But you know, I mean, it really, like, I don't know like a lot of the low-level details of this, but like I do know that like the Java interface is like not preferred by a lot of people at this point. I don't know how much of the low-level stuff is actually done in C or another like lower-level language, but we kind of need a new version of this. And as you can see, like, this isn't updated extremely regularly. This is from 2015. And so there's various things to try. New experimental. Oh, there's a Jython version. I have some experience with Jython. It's like the little Python like snake coming up out of the coffee cup, and it's a thing, but it's not really actively maintained either. And like this is just we need. I think we need a slightly more modern version of this. Yeah. I don't know that anyone's currently got any money to do this. I don't know if there's any grants around. I don't know if I really want to apply for one specifically for this, but it would be really useful. It's something that the community needs as an updated version of this thing that's compatible with Sage or some other like more modern kind of interface. So here's a semi-technical description. Oh, we are in the process of rewriting this. Okay, so I hope that it's still in the process of being rewritten or something. Okay. Like, yeah, I don't know. Maybe I should just email Matt Valeria and just be like, hey, what's going on with this thing? I would like to know this, actually. I should find out about that. All right, anyway, let's see what else is going on here. Okay, so there are descriptions of some of the algorithms here, which is good. Oh, more coming. It's encouraging. Okay, yeah, so, this is a good book. All right. Anyway, that's the Universal Algebra Calculator. I hope to have some version of some of those algorithms that actually is just natively part of Sage at some point. That would be nice. But yeah, well, I have 30 minutes left in the stream, and I didn't do what I wanted to accomplish, but I did have a good realization here, which was nice. And I still find it very neat that many of these things are simple. I think that that's really cool. Yeah, and so that's definitely a nice thing. Oh, what was the oops? Oh yeah, that I didn't do what I intended to at all. But that happens a lot of the time when I do these streams. And people have good questions. There's good discussions. I got to learn what Pop Tropico is about. I mean, maybe Nova told me at some point, and I just didn't. I didn't remember the details. I just remembered that it was a thing. But yeah, I mean, it's been cool. Let's see. Is there anything that anyone's wondering about, or did you start the tangent? I don't remember anymore. So the original thing was that I was giving examples of the construction, and that's what this was. And then I was talking about like the question that I wanted an answer to. And so, okay, if nobody has anything that they're curious about, I'll say like what I was preparing to talk about. Of course, 3 hours is never enough. I always need 3 more hours to actually do whatever it is. And I guess that's part of being a professional, mathematician. It's always it turns into this thing where you're like, okay, look, it's very simple. I can't believe nobody ever came up with this before. And then you start explaining it. But in order to start explaining it, you have to explain all these other things. And then finally, after like 8 hours, you're like, all right, so now you're ready to begin knowing about this thing. And then when you start explaining it, you realize like 7 different things that you didn't realize before, but those are all obvious too, and they each will only take a few hours to explain, and before you know it, you're like 40 or 50 years old, and that's what you've been doing for your entire life. And I hope that that's what happens to me, because I'm not that old yet, but I will be soon, and I'm sure that I really hope that it's just full of exactly that type of thing forever, because it's great, it's fantastic. Yeah. So I wanted to use this theorem. I spelled this name wrong, I think, but I wanted to use this theorem in order to construct these quasi-groups, or when you did R construction to them, they became whatever genus surface you wanted. And it turned out that it was possible to do that, and as we realized today, just messing around, apparently we have an upper bound which sorry, I'm starting to think about if I can prove that this is actually sharp. No, I don't think I can. I don't think I can without doing additional actual work. Okay. Well, anyway, we have an upper bound on how many elements a finite quasigroup would need in order to be able to be used to do this construction and get a surface of genus n, closed surface of genus n. And we got this bound that was this ridiculous formula. And so that's, that's something. And then I had said, really though, I care about the higher dimensional version of this. So the thing is, when you go to ask this question, what question? So the analog of this question, can we find a quasigroup so that the serenation of the quasigroup has a component of genus n? There's a higher dimensional version of that, and the higher dimensional version of that is something like, if you give me a certain manifold that's a higher dimensional manifold, it's like the 3D or 4D or like 17-dimensional version of what I just did here. If you give me a higher dimensional manifold, that it has to be orientable, it has to be triangulable, there's some assumptions. Can you find an algebraic structure that will play the role of the quasigroup here? So that when you do our construction to it, you get a component that is the manifold that you started with. Can you make every manifold by doing this? And so in general, we don't even want just finite things, like things that are closed like this, but things that can go off endlessly or whatever. And the answer, that's the main theorem of the paper that I was going to work on editing, is that yes, you can actually do that. And the way that is that there's a construction that will actually create the algebraic structure that you want for the higher dimensional ones. It's not as nice as the one that I showed here, in the sense that even when you want to make a shape with a finite number of triangles, you need an infinite number of elements. So the answer is like kind of a cheap answer that is infinite instead of finite. That somehow makes it easier. But I wanted to clean up the proof of that to make it more readable, because the referee wanted it to be presented more nicely. And I think that I really can clean it up. I don't think I can make a reasonable start in the next 20 minutes or so, but that's where I wanted to go. Because the idea is that we don't understand higher dimensional manifolds quite as well as we understand the two-dimensional ones. And so if we can understand them by understanding these algebraic structures instead, which I claim that we actually can understand quite well thanks to tools from universal algebra, then we can use that to get a better understanding of topology. And so that's something that hasn't really been explored, yet, like prior to this. So that's where I was going to go. I did remember one other thing I wanted to try, though, which was, so I had written some code. Okay, these are all the prime ones, whatever. But okay, so the sequence of the orders of these things that I get goes 85, 103, 121, 133. I'm going to type those numbers into the search engine for the Encyclopedia of Integer Sequences, and I'm going to see if I get anything interesting, which I probably won't, because that's just life, but I'm going to see if I get anything interesting. So 85, 103, 121, 133, 12, oh no, that's 1225 is next. Alright, I'll just try these four terms. Nothing. Well, approximate matches. Three, 4, 5, 6. Alright, that was fine. Okay, so none of these are exact. They have they have tools, transformations. multiples. Okay. Let's see. And minus 1 after draw. Okay, well, all right. For odd, I mean, it's unlikely that any of these are matches. If I add more terms, I might be able to get something slightly more interesting. Let's see if that helps. I mean, I know there's no sequences that match it, but that was 4, 5, 6, and 7, right? Okay, so 6 was 133, 7 is 151. Okay, and then 169. And then, let's see what comes after that. 181. So we still shouldn't get anything that matches perfectly. Constant differences. Well, okay. I know that it's basic. I know that it's basically linear, so that's not shocking. Let's see. Yeah, it's I know that it's basically linear. Like that's okay. Let's see. Yeah, I mean I could mess around with these forever, but it seems like there's no exact match. That's fine. The one other thing I want to try, just in order to make sure that it's not like some really wild thing that I just have not noticed before, but let's try just the sequence of maybe the orders, the number of holes in the surface where you get a prime order. Let's just try that just to check that out. No exact match. Two character edits. 4, 7, 9, 10, 11, 12, 13. Oh, then it goes 17, 19, 20. Yeah, okay. Polynomial. Transformations, nothing probably too exciting. Let me add a few more terms and see if it says anything else or if anything sticks around. 26, 28, 30, oh, I wanted 30, 31, 34, 36. Nah, it's got nothing. None of these sequences show up anywhere. Well, that's okay. I mean, that's life, you know. It's not too hard to find an integer sequence that's not in the encyclopedia. It's always a cool surprise. Yeah, it's always a cool surprise when you find something that's in the encyclopedia. No, I understand. So it's not ridiculous exactly. Of course, there are literally an infinite number of different integer sequences, and there's no way that they're all in the encyclopedia because it's a finite, thing that we have. We keep adding to it, but at any particular stage, it's finite. But of course, it's natural to say, well, there's only so many types of patterns that you can come across. And of course, many of those are going to count the same thing in different ways. And, that's very reasonable. And so it's true that if you're studying some kind of combinatorial object, many times you'll be messing around with it and you'll be like, really this is just partitions. It's just, multi-sets. It's just, triangulations of manifolds, like whatever. Like you'll find that there's only certain things that come up over and over again, right? Like that's reasonable. But it's still the case that just messing around, you can find sequences that have no known interesting combinatorial interpretation that are not in the encyclopedia. Like but that are an interesting sequence. Like that's very, very possible. They don't just accept anything either. I'm pretty sure that things that should be in there are things that have a reasonable amount of interest, awareness, because it's like Wikipedia, right? Like you can't make a Wikipedia article on every person. Like that's just not practical. most people don't have enough secondary sources on their life in order to have a Wikipedia page about them. You're not going to be able to make a well-edited encyclopedia that way. So yeah, I mean, it's not ridiculous in the sense that, like, there's only so many sequences that tend to come up a lot that are very interesting to us, like the Catalan numbers that I mentioned before. Yeah, well, it was worth trying, though. I don't think that, well, okay, there's one other thing I could give a shot, I guess, which is typing in the prime numbers that appeared for the numbers of elements and putting in that list of primes. So I guess out of an abundance of caution, maybe I should do that. So 103, 151, 181, 199, 211, 229, 241, whatever. After removing the first term, okay, let's try to add some more to it because that's something. 271, 331, 373. Nope, it's nothing. Okay, this is not. Yeah, none of these are that closely related. All right, whatever. Yeah, I don't think any of these are really super thrilling. Let's see. And is the denominator of the fraction given that x plus y equals 1? Well, let's see. So what is this saying? The denominator of the fraction x to the n plus y to the n, given that x plus y equals 1 and x squared plus y squared equals 2. And how is this transformed into this sequence? Transformations of the original query. Okay, just some transformation. Okay. Well, yeah, I'm not really sure about that. None of these seem like blatantly obvious to me that there's anything especially interesting going on here, but that's fine. All right. Yeah, I think I've had about enough of the encyclopedia for right now. But yeah, so if there's anything interesting to these numbers, it remains to be seen. But yeah, I think that today was really a victory. We found this formula. I'm going to find some examples at some point. I'm going to find a program or implement a program and actually generate some examples and fiddle around with them. It'll be cool. Yeah, we did it. We did it, chat. we found this formula. Yeah, if I actually, so I'm probably not going to add this into the paper that I'm already doing edits on, because I shouldn't add anything new. I should just clean up what's already there. So the editing process can end, and it can be published. Yeah, I mean, I'll have to put like a thanks to the Twitch chat or something, though. If I put this into a paper at some point, I'm gonna have to be like, thanks Twitch, we did it. Oh, I remember people joking about corporation, people have ads in the sense that, people will say in their paper, oh, this was due to, thanks to NSF, NSA, whoever, for giving us this grant, but I've seen people joke about corporations doing this in just completely academic settings, but this is how they get you, is because you use their service and then you're like, I found this, when I was streaming or whatever, and then they get their ad in. How do they know who the people were if they were anonymous? Did they sign their work somehow and then have them did they sign their work cryptographically somehow and then verify that it was them later, or Because like anyone can just claim that this is the super permutation thing, right? I'm sorry, I don't understand. So you're saying the this is the super permutation thing, the anonymous results about super permutations. Are you saying that your professor was one of the people, or just that they may? Okay, you're saying that they were one of the people, or they weren't. I don't know. I mean, anyone could be, you know. I've actually never worked with these things though, so it couldn't have been me, that's for sure. But yeah, I mean, if there's no proof, you know. Oh, I understand. Right. So I forgot because I never followed this very closely. Okay, so there was a paper in which that result was actually published, and they credited the anonymous person with the result. I understand now. Oh, cool. Yeah, I mean, these days, you know, who knows where these things come from? It's a mystery. Yeah, it's okay, buddy. No one's, you know, your results don't have to be anonymous. You can still get credit for it, Dobby. Dobby, of course, is the lead author on all of these things, of course, you know, because he's a good dog. Yeah. Well, anyway, yeah. That's true. That's why our finances are in such great order, is because Dobby does our taxes. He's only like 35 in dog years, but he's really proficient. He's deeply knowledgeable about these things. You know, we ask him about interest rates and stuff, and you know, and he says rough or some variation of that, and we're like, yeah, you know, the market's been all over the place. It's great. I apologize for that. I'm really sorry, but you know, I make corny jokes sometimes. Well, you know, I think this is probably a good stopping point. I'm really pleased that we have this calculation. I'll be less pleased if I later discover that I dropped a minus sign or otherwise made a mistake, but at the moment I'm feeling really good about it. I really appreciate all of your great comments and questions and discussion. It's really what makes the stream go so well. Like that's you know, a huge part of it. Yeah, I mean, is there any last thing that anyone wants to ask that I can do in 10 minutes? Not everything takes 3 hours, believe it or not. Well, if not, I'm really glad that I was able to actually do all of this today. It's not what I planned, but some of the best things happen when you just didn't plan for it to happen. That's just how life goes. And so this has been really cool. I have lots of good links, I feel like, that I can post in the video description when I post this on YouTube. So there's going to be lots of cool links, and yeah, it should be pretty awesome. Well, I guess maybe I'll sign off a little bit early then, since I think that this is a reasonable stopping place. But thank you all so much for a great evening or morning or middle of the day or whatever where you are. I'm sure I'll post on Mastodon about what I'm actually doing for the next 2 streams, whether it's going to be some kind of rerun or I post something else. You know, it might not be me live if I'm not able to get up and do this, you know, at 7 in the morning, because for me, 7 in the morning, because I'm moving to a different time zone briefly. But there will be something for sure. So I hope to see you, well, soon. I don't know about there because maybe I won't be there, but I hope to see you at some point in the not too distant future. I'll definitely be back streaming live 3 weeks from today. Oh yeah, Nova will be there regardless because yeah, it'll be good. So yeah, well, thanks everyone so much again. I hope that you had a really awesome time, that you had fun, that this was a healthy distraction from doing your homework or whatever else it is that you needed to do. So yeah, I'm really looking forward to it, and I hope to have lots more cool mathematical content coming to you in the not too distant future. So thanks everyone so much again. Yeah, I'm gonna head out now. But yeah, make sure to have a great rest of your day, your night, your morning, whatever it is, when and wherever you are in the world. All right. Well, until next time. See you.